All right, this is part 2 of section 9.2. Now we're going to simplify trig expressions using algebra and the identities that we know. Okay, so cotangent of theta and sine of theta. So I'm going to take both of these, just write them down, and then I'll look at cotangent, and I know that I can write it as cosine over sine because of the quotient identity right here. All right, so I'm going to replace cotangent with cosine of theta over sine of theta times sine of theta over 1. And I put it over 1 just to make sure I know that the sine is in the numerator. So I got a sine in the numerator and the denominator, so they cancel out. And I'm just left with cosine of theta. So we have simplified this expression to cosine of theta. Okay, if we look at this one, we have sine squared of theta, cosecant squared of theta minus 1. Now, whenever I have a trig function that is squared and then a minus 1, I would always go back to the Pythagorean identities and take a look at them. And let's see, notice there's a cosecant squared and then there's a 1. So if I can manipulate that just a little bit, I can get that equal to cotangent squared of theta. So let's do this. There's my identity. If I subtract the 1 from both sides, then cotangent squared of theta is equal to cosecant squared of theta minus 1, which is this part right here. So we know that this part right here is really just equal to cotangent squared of theta. So if we get rid of this, so now I have sine squared of theta times cotangent squared of theta. And we know that cotangent of theta is equal to cosine of theta over sine of theta. But if I square this side, I'll square this side as well. So that'll give me cotangent squared of theta. And now the square is going to go to the top and to the bottom. So this would be cosine squared of theta over sine squared of theta. So I'll have sine squared of theta times cosine squared of theta over sine squared of theta. I'm going to put this over 1. Well, hey, the sine squares are going to cancel. And then I'm left with cosine squared of theta. And that'd be our final answer. We have simplified this expression right here. Okay, if we look at this one, 1 plus tangent squared of theta over 1 plus cotangent squared of theta. Now, same thing, I've got a squared trig function and I've got a 1. So I would take a look at my Pythagorean identities. I'll write them over here. 1 plus tangent squared of theta is equal to secant squared of theta. And 1 plus cotangent squared of theta is equal to cosecant squared of theta. Now these are just, we don't have to manipulate them at all. We see that 1 plus tangent squared of theta, well, that's just secant squared of theta. And then we see 1 plus cotangent squared of theta, which is right there. That is cosecant squared of theta. Okay, and now what I'm going to do is I'm going to separate these out. So secant squared of theta times 1 over cosecant squared of theta. Well, 1 over cosecant squared of theta, that's the same thing as, get this written down, sine squared of theta. And then what I can do is I can rewrite this as 1 over cosine of theta. So 1 over cosine of theta times sine of theta. So now what I have is sine squared of theta over cosine squared of theta, which, remember, tangent is equal to sine over cosine. But if I have a 2 here, I'll have a 2 here and here. If I have a 3 here, I'll have a 3 here and a 3 here. Okay? So what this is equal to is tangent squared of theta, and that will be your final answer. Then last but not least, expand 4 cosine squared of theta minus 1. Okay, so remember that a squared minus b squared is equal to a plus b times a minus b. So what I'm going to do is I'm going to try to make this look like this. So I have a 4, I could write 2 squared. My cosine is already squared. Minus, if I square a 1, it's still going to be 1. So then I'm going to take 2 cosine theta, raise both of them to 2, minus 1 squared. Well then now a is the 2 cosine squared and the b is 1. So using this format right here, what I have is 2 cosine theta plus 1 times 2 cosine theta minus 1. And this would be our final answer.